Welcome back to part two. So we're still talking about the wave nature of light. And in these notes, we're going to do a couple things. One, we're going to show how Thomas Young proved that light is a wave. Two, we're going to try to understand what's happening when you take light and you shine it through two slits. Later, we're going to look at what happens when you shine light through a single slit or through a diffraction grating, which is thousands and thousands of slits together. But for these notes, one, how do we know light is a wave? And two, what happens and why when you shine it through two slits? So let's go back to 1801. Think about that. That's a really long time ago. Ohio became a state in 1803. So this is going on even before then. But this dude, Thomas Young, did the first experiment that was recorded, at least, that shows that light is a wave. So what happened was he took light and he shined it through two thin slits that were placed really close together, and he saw what was called an interference pattern. And we're sort of working by a little bit of extrapolation here, but the long story short is if you take water and you shine water through two slits, or you have a wall with two openings and you launch water at it, you will get a pattern where you'll get some areas where there's constructive interference or waves that are taller because the waves from the two slits add together positively. And then you'll get some areas that are actually flat. If you didn't watch the Veritasium video from the last folder on Schoology, he has an excellent demonstration where he actually does this out on a pond with two sources of waves. And you can see some of them are perfectly flat. Some of them have higher amplitude. So to go back, what's really going on here? Water waves are waves. We know that because they're waves. They can add together constructively and destructively when you shine them through two slits. So if light can add together constructively and destructively when it goes through two slits, then it must be a wave because it does the things that waves do. That is all that's going on here. We create experiments where light is put in a wave position and it does the things waves do. Therefore, light must be a wave. So here's what happened. He basically took this card that had two really thin slits on it. And the question is, what would he see on the other side? A lot of people would probably predict that you would see this. Two slits. And because you have light going through two things, you'd think it would just go right through and sort of project an image of that on the other screen. That's what would happen if light was a particle. More on that down the road when we get to quantum. But instead, he saw this. Lots of lines, more than just two. The one in the center, sort of between the slits, was brighter and a little bit wider. And then there were a bunch of other lines off to the side. So that's what we're going to try to explain today. Here's a view of that experiment from the top. And what you're seeing here is just a subset of the different waves or the different rays of light that are going through those slits. Remember, it's okay for us to zoom in and sort of pick to look at a couple of these rays at a time because the light that's propagating through here is a wave. So imagine Huygens principle with a wave front, and this creates two little ripples of waves going out, and those ripples are going to continue to propagate until they hit the screen here. But you can see two of them, or the two that if we choose just to focus on those two that go right to the center, create a bright spot here. And then when we look at different spots to the side, sometimes those waves reach that spot in phase. See how these waves are completely lined up. So they add together constructively to give you a bright spot. And sometimes they get to other spots on the screen out of phase where they cancel each other out and give you a dark spot. That's what we're going to look at here. So here's a picture of an actual interference pattern from a couple slits. And you can see that there's a bright one in the center, and then we have dimmer and dimmer slits off to the sides. Here's what I was trying to explain on the last slide, or two slides ago. If we have a wave front and then we send it through two slits that are thin and close together, Each one acts as a source of ripples, and the ripples from one slit are going to overlap with the ripples from the other slit. In some places, those are the ones where you can see the blue lines here. Those waves are going to add constructively, crest with crest, trough with trough, to give you bright spots. And then in some places, these in-betweens, the waves are going to be out of phase and they'll give you dark spots. That's basically all we are trying to explain today. This is the same experiment with water. So these are two sources of water, and you can see they are literally creating ripples. You can see some areas, these would correspond with bright spots. So the one right in the middle, and then sort of alternating as we go out, you can see big ripples. So those are high waves. If you looked at it from the side, you'd see these waves are higher than the individual waves made by each source because they're adding together at those points. And then when they're out of phase, you have these lanes in between where the water's completely flat. And that's something that you can see perfectly in that Veritasium video from the last folder. So if you didn't watch it, check it out. Pause these notes. It's probably more important than what I'm talking about right now. So you can see that there are bright spots, constructive interference, and then flat lanes in between. Here is a video of that happening. So again, these are waves in water, just trying to see what waves do. Let's see if we can skip ahead a little bit.
When a plane wave passes between two openings, the result is like creating two new waves. These waves can add together to form new waves, which is called superposition. When the two waves are out of phase with one another, they add together to create no wave. This is called destructive interference. These red lines show where destructive interference is happening. When the two waves are in phase, they add together to form an even larger wave whose amplitude is the sum of the amplitudes of the two waves. This is called constructive interference. These green lines show where constructive interference is happening. You can think about how this experiment might prove that light and sound are waves.
So that's water. I know it's kind of hard to see in this picture, but you can see flat lanes in between. Those are destructive interference. And then big waves in the middle, that's constructive interference. The basic idea that you should be more or less on board with so far is when water waves pass through two slits, you get constructive and destructive interference alternating as we go out. Therefore, if we get the same thing when we pass light through two slits, light is also a wave. That's the kind of thinking Thomas Young was doing back in 1801. So to summarize, we know that waves show constructive and destructive interference when they pass through double slit. Light shows bright and dark spots when it passes through double slits. Therefore, light must be a wave because it does the things that waves do. Super cool. Now we're going to try to understand a little bit more of why we see the bright and dark. And there's one little pretty harmless equation coming along too. So of all the bright and the dark spots that we can see on the screen when we shine our light through these two slits here, forget about all of them except the one right at the center. So there are lots of ripples. You can imagine them as ripples propagating out, adding together, but we only care about the point right at the center. So that appears as a bright spot with two slits here. So imagine as light passes through these slits, it diffracts. So diffraction is just the bending of light as it passes around an object or through a slit as it moves towards the screen. We're just going to zoom in on the light that reaches the center. So the light obviously spreads out, but we're just going to zoom in on these two rays of light, one from each slit. They happen to be the ones that reach the center of the screen. Because the center is exactly halfway between the two slits here, both of these rays of light travel exactly the same distance to reach there, which means they're going to arrive in phase. If they started in phase from the wave front that they came from, you'd assume that they're still in phase after they travel the exact same distance. Nothing would cause them to launch forward or behind phase. Because they get there together, this is like adding two up waves on a slinky. They're going to give you a bigger wave because they're in phase. So here you go. You can see the picture. Same distance, in phase, gives you a greater amplitude. Now we're going to pick a random point on the side of the screen. We're going to call it point P. For some of those random points on the side, sometimes you see a bright spot, sometimes you see a dark spot. Let's try to explain that. The first really important thing to understand is if we look at the rays that go to a random point on the side, point P, one wave always has to travel farther. The two rays travel different distances to get to point P. The center, they always travel the same distance, but on the side, they always travel different distances. So for any point up here, the light from the lower slit has to travel farther. For any point down here, the light from the upper slit has to travel farther. So this extra distance, so if we drew a line across here, somewhere about there, everything from there on up is the same distance for both. But this extra distance, this last little portion down here, is the extra distance traveled by the blue wave or the second wave. So we are just going to look at a special case for what if this extra distance just happens to be exactly half of a wavelength. So if it's exactly half of a wavelength, you can see that the blue wave gets to that point a little bit later. Why does it get there later? Because it has to travel farther. If they started here at the same time, but the blue has to travel a little farther, it just gets there later. But also because it has to travel a little bit farther, it gets there out of phase. If they started in phase, but blue has to travel an extra half wavelength, you can see that here. Red got there first. Blue had to travel an extra half wavelength, which shifted its phase off by 1/2 lambda, which means these two waves are now completely out of phase, and you see a dark spot at point P. The same thing is true for the special case where that extra distance traveled by the blue wave happens to be 3/2 lambda or 1.5 lambda. So now you can see the blue wave gets there even later because it has to travel even farther. So here would be 1 full wavelength later plus an additional half wavelength. They're still out of phase, so it appears as a dark spot. And that pattern continues on and on and on as far as you want to go. So if the extra distance is equal to half a wavelength, 3/2 lambda, 5/2 lambda, or general format, m plus a half times lambda, for all those cases, one wave is shifted by half a wavelength, so the waves reach out of phase, so you see a dark spot. That explains what happens with the dark spots. Similar thing, we're still looking at some random point P on the side, but now what if we just look at the points where that extra distance, so remember here, this extra distance down here that the blue wave has to travel, what about those special cases where it is exactly 1 wavelength or 2 wavelengths or 3 wavelengths? Well, the blue wave still is going to get there a little bit late, but if it gets there late and it has to travel exactly 1 more wavelength, you can see blue here, 1 full wavelength behind still puts it in phase. Even though it got there later, it had to travel a little farther. But if the extra distance is a whole number multiple of lambda of the wavelength, it gets there in phase, which means the two waves add together constructively to give you a bright spot. That's true whether it's exactly 1 wavelength, extra distance, or 2 wavelengths, extra distance, or 3 or 4. So to state that generally, anytime the extra distance is m times lambda, or a whole number multiple of lambda, one wave is shifted off by a whole wavelength or 2 whole wavelengths. They get there in phase, and you see a bright spot or constructive interference. Now to tie all that together, we are just going to try to mathematically calculate how far is that extra distance. We can put a number on it based on the slits and based on the screen and all of that good stuff. So back to our general screen diagram here. The two rays of light converge at the same point, but the bottom ray here has to travel an extra distance. Because the screen is so far away compared to the spacing of the slits are usually going to be millimeters apart or less. We can assume that they're basically parallel. So the extra distance traveled by the wave is just going to be this section from the dotted line down to the slit. From everything else up here, the waves are going to travel the same distance. D is the distance between the two slits. And then theta here is the angle right from the center of the screen or from one of the slits to the point that we're looking at up here. Next, if we zoom in on those two rays, so the screen is so far away that these two rays to get there look like they're parallel to us, and we can assume they're parallel. Theta, remember, is the angle to the screen. So we want to find this additional distance down here. Well, first of all, you can do a little bit of geometry to prove that this angle in here, when we look at the little triangle that's created by that extra distance, this angle theta is the same as this angle theta over here. You could see that because this angle theta is complementary to this one, which means in a right triangle, these two angles have to add up to 90. So this theta is that theta. If that doesn't make sense, I can explain that in more detail, but this theta, same as that theta. So if that is true, this extra distance is just equal to d times the sine of theta because it's a right triangle, and that is our SOHCAHTOA trig identity right there. So d is the hypotenuse times the sine of theta, gives us the extra distance, boom, down there. So then what do we do with that? We have this equation, which is on your AP equation sheet, and it'll be the equation you use anytime you have a double slit diffraction problem. D is the distance between the slits. Sometimes that's called the slit spacing, measured in meters. Sine theta, remember that's the angle from the middle out to the point that you're looking at. M is the order of the fringe, which is just going to be a whole number. So 1, 2, 3, 4, 5. And then lambda is the wavelength of light. We have to consider the wavelength of light because the extra distance being a multiple of the wavelength is going to be different if we look at different wavelengths of the light. So what do we do when we actually use this equation? Well, you have to remember that d sine theta, the left side of the equation, is equal to the extra distance traveled by one of the rays. So if you want to find a bright spot, set the extra distance equal to m lambda, a whole number multiple of the wavelength. If you want to see destructive interference, or you want the waves to be out of phase and cancel each other out, you want to set the extra distance equal to half lambda, 3/2 lambda, or 5/2 lambda, which just looks like this. So if you leave the equation the way it is as written, d sine theta equals m lambda, and use a whole number for m, that gives you bright spots because extra distance is equal to lambda or 2 lambda or 3 lambda. Waves arrive in phase. They add together to give you a bright spot. If you change this equation and instead of m lambda, you do m plus a half times lambda with values of 0, 1, 2, etc., you will get extra distance is equal to half lambda or 3/2 lambda or 5/2 lambda, which means extra distance is equal to shifted off by half a wavelength. Waves arrive exactly out of phase and you see a dark spot. So that explains why, if you use this equation, right in the middle, that would be the central fringe or the 0th order. You see a bright spot. Your next bright spot would be 1 d sine theta equals 1 times lambda. d sine theta equals 2 times lambda, 3 lambda, 4 lambda, etc. And then the dark spots here, you can find those by substituting in d sine theta equals m plus a half lambda. So this would be d sine theta equals 1 half lambda, d sine theta equals 3 halves lambda, d sine theta equals 5 halves lambda, so on and so forth. That's a lot to take in. If you're confused, I posted a couple videos in the folder that'll help walk you through double slits and kind of explaining the math behind it. Next week, I promise we will do a plethora of examples. So hopefully by practice and repetition, things will start to make more sense. In the meantime, thanks for watching, and I'm happy to help out if you have any questions.